Just in the program, so very glad that Amy accepted to give the first talk, and Dick is going to give the second talk, and Jose Luis the third talk, and Anna is going to talk tomorrow, hopefully.
Okay.
Is she better?
I mean, she was on her feet yesterday.
Okay.
I gave her soup. The soup that, yeah.
Yes, yes. So in the spirit of talking about the future facilities, we have Amy, and she's doing
Ami.
Amy.
Yeah.
Sorry.
It's okay.
Sorry. Amy. Sorry. So Amy is going to talk about Roman. Thank you, Anne.
Sure. Yeah. And thanks so much for the invitation. It's really great to be here. Yeah, I haven't actually been in doing work in Sao Paulo, but I did pass through on the way to a DES meeting in Campinas about 6 years ago now. So long time ago. So it's great to be actually here. And then, yeah, so Roman, you might not have heard that much about it. I guess, yeah, everybody's probably heard of it to some level. Is that roughly true? But since it's a relatively small group of people working on it currently, mostly US based, but not only US, we have partnerships with other places in the world, including, for example, France, Japan. So it is also an international project in many ways, and I'll come back to that, or yeah, we can also discuss more about that as we go into discussion later. But yeah, today I thought I would just give you a broad introduction to the Roman Space Telescope, tell you what it's designed to be capable of doing, and then where we are in the process of building it. So we're on track to launch in about 2 years. So we're still in the process of putting everything together. But yeah, I think it's going to be really great for cosmology, and also a lot of ideas, I think, related specifically to fundamental physics, I think will be something we can explore with Roman. And that's an area that maybe would be great for further discussion. And the other thing, I'll give a little caveat, which is that there's a lot of instrumentation and measurement side of things in this talk. So I know most of the audience here is primarily theoretical, but it is pretty interesting to actually try to, bridge the two, see what the actual instrument is capable of, and then you can also then brainstorm to what kinds of physics tests do. So hopefully it's not too much of the things that you never wanted to hear about, but there will be quite a bit of that. So in general, so I'll start with the background of the Roman Space Telescope, put it in some context for all the other large-scale structure surveys happening at a similar time, and then some examples of how we prepare for the actual measurements with Roman, and then some comments on the path toward science. So yeah, these are individual parts. So yeah, usually I would start talks with some big picture, but we don't have to spend too much time here because we've already covered it in the last day. But in general, we're all thinking about, does some sort of lambda CDM model, so something with dark matter and dark energy and maybe only 6 parameters, does that really explain all the history of the universe from the time of the cosmic microwave background to now? So Roman will be looking at this, where the large scale structure is, and yeah, so that's one of the big questions that we have. Now I'm going to very quickly switch gears to our very local universe, because Roman Space Telescope's other big science goal, which is to look for exoplanets and do statistics of exoplanets. So many of you may know, back when dark energy was discovered in 1998, that's kind of what set off a lot of these investigations, including, more impetus toward the Rubin Observatory, but also at the time it was called WFIRST. So you might see that acronym. It was the Wide Field Infrared Space Telescope. And that also evolved from earlier dark energy missions. So you might have also heard of JDEM, that was the Joint Dark Energy Mission. That would have been together with the Department of Energy. But yeah, there was some evolution from the cosmology side to what we now call Roman. At the same time in the 90s, there was the first exoplanet discovered, and then a bunch of exoplanet missions, both from the ground and space, but the ones on this graphic are other NASA missions, so Kepler, and also the Transiting Exoplanet Survey Satellite TESS. And this picture gives you a little idea of where exactly they're looking. So, this is all within our own Milky Way galaxy. And Kepler and TESS before had a very kind of like narrow perspective. So Kepler's the green out there. I think TESS, you can't even really see. It's just kind of like an inner part just near the green. And Roman is really looking out. It's going to be looking toward the galactic bulge, and it's really going to increase the parameter space. Specifically, if we think about like the orbital distance, so the distance from the exoplanet to its host star, and then also the range of planet masses. So the plot on the right is taken from some work done by Matt Penny. And this shows you with our solar system planets on the same graph, what is the kind of statistics that Roman will get us for exoplanets. And so we see that all the previous experiments, and actually I don't think TESS planets are on this plot because they're even smaller on the x-axis. But in general, we're looking at a much broader distribution, and we're trying to understand, how many Earth-like planets or Neptunes or Jupiters would we see out there. So really taking a census. So there's some aspect actually there where the statistics that are done for exoplanets, there might be something actually in common with the kinds of things that we think about for cosmology. And then, the one on the left is kind of another picture of where we're looking specifically in that orbit.
So, just a curiosity, for searching for exoplanets, they're looking for the dip in the luminosity or the spectroscopic change?
Right. So dip in the luminosity and also an increase in the luminosity. So that brings me to the main method that we'll use with Roman, which is microlensing. So all of you know about gravitational lensing in general. We mostly think about it from the perspective of galaxies lensing the light of other galaxies, or clusters lensing background galaxies. But you can also have lensing with stars lensing background stars. It's a very similar, the same concept, really. And so there's a schematic here that shows you what happens for the light magnification of the background star based on the mass of the foreground star. And these things are all kind of moving. They're very nearby, so there's some motion. And as they kind of pass into alignment, it will brighten. And then as it passes out of alignment, it'll get dimmer again. But if there's an additional mass orbiting around that foreground star, then you might have another small peak in that brightening. So that's how we might detect exoplanets that way. And because it's really about mass, you get a lot of information there that is complementary to the kinds of, so Rogerio just mentioned, you can also see a dip. And of course, that's when the planet passes in front of the light of that star. And so instead of a magnification, you see an absorption of that light. So that method is called the transit method, and that will also be really helpful with Roman data. We'll also get that method. So really there's two methods here, microlensing and transit. So transits, we think based on simulations, it could uncover something like 100,000 new exoplanets. So it's a huge jump from, I think currently we're at something like 3,000 or 4,000 planets that have been discovered so far with the transit method. And that by far is the most productive method of discovering exoplanets. But yeah, there are other methods. There's also astrometry, so like little changes in the motion, or radial velocity, which is the wobble in the motion.
Can I ask you something?
Yes.
So I guess both the microlensing and the transient will be looking at differences in the magnitude of that one for magnification. I don't know if I understand correctly, but microlensing is because the tension is changing when the planet is.
That's right. Yeah.
And how is the change in magnitude that this telescope will be able to?
Yeah, so one thing I haven't mentioned yet, which is that, so these measurements have to be done by repeat measurements. So there's a cadence of, I think it might be every several times a day. So some number of hours, you repeat the observation and you look for that change. So you get, the data that you get is basically luminosity as a function of time. And so, yeah, you do have to be very precise for that flux measurement. Yeah, I'm not sure exactly what by percentage you have to be, have that. I would guess maybe on the order of like 1% being able to just measure the stable flux subjects. Okay, so
One more question.
yes.
Are you also sensitive to what's called microscopic halo objects, macro?
Yeah, so I was actually just going to mention that, which is that, so in addition to foreground stars, you can get micro lensing from also free-floating planets, it's mentioned here. And if, yeah, depending on different theories about free-floating planets, so things that are not necessarily associated with a star that they're orbiting, we might be able to detect a bunch that way, also with Roman, but also you could have black holes. And actually, so one reason to mention this at all is because people have thought about measuring or trying to put some constraint on primordial black holes. And that obviously has a very good connection to things like inflation and models of the early universe. And so that's, yeah, I wanted to mention this because it's part of a bigger ecosystem of cosmology. So even though, you know, we don't necessarily study exoplanets, actually some of these techniques might be useful for studying fundamental physics and cosmology too. So yeah, I don't know that much about that work, but I know there's at least a paper on things like primordial black holes. And I think people in general have thought about, yeah, machos and what kind of constraints we could get. Yes, so yeah, so again, you know, it's kind of a weird combination, cosmology, exoplanets. But here are the requirements, you know, once you're interested in those two topics that you need from an observatory. So for the cosmology side, angular resolution, so really that, like, you know, the fine details of the image. Here, near infrared sensitivity, that's useful for things like looking out to higher redshifts, and also it's less sensitive to dust. So that's really important to get infrared, as well as the optical data that we're already getting from other experiments. And then photometric precision, so relating to some of the questions and discussion earlier, you know, exactly how well we can measure that light. And then also stability of the point spread function. So Roman won't necessarily have like a better point spread function than, say, James Webb Space Telescope, but it will be stable across a really, like it's designed to be stable across a wide field of view. So that's the special aspect of Roman. And then for the exoplanets or microlensing side, you also need the observatory to be agile. So, you know, you want to point it at a different place in the sky and have all the hardware be settle very quickly. So that you can then take data which isn't, you know, kind of affected by some sort of moving of that observatory. And then similar to cosmology, you also need that very precise photometry measured. And you also, you care about the field of regard. So where you can point exactly as you're looking into, say, the Milky Way galaxy to look for lots of planets. And maybe another thing, you know, we mentioned blending yesterday. So for microlensing, I guess, yeah, maybe should have also mentioned angular resolution there, because when we look for exoplanets, we might be looking at stars, and in the galactic bulge, it's a very dense region. And so that can actually be really hard to do from the ground, you know, looking at these very crowded fields. And so having this very like highly resolved objects is really, really helpful. All right, so that's then where we get to Roman. So Roman was the top-ranked large space mission in the 2010 decadal. So it's the next astrophysics mission to follow the James Webb Space Telescope, which, as you know, launched 3 years ago. And yeah, so you can think of it as a Hubble type of telescope, but with a much wider field of view and also more agile as an observatory. So it has the same size diameter mirror as Hubble, but the what you can actually take with a single snapshot of your camera. It's 100 times as much. And as I mentioned, yeah, it will study dark energy exoplanets in general, infrared astrophysics. All right, so there's a comparison. Sometimes, people wonder, well, why are you doing another space-based infrared telescope after JWST, which was, very powerful, but also took a long time and to build. And yeah, so why do we want another one up there? And so here's a comparison of the mirror diameter on the left and then the field of view on the right. So JWST is clearly much more powerful at collecting, as a light bucket. It collects much fainter photons much more easily. But the field of view, so the detectors, when you're looking at the sky, it's a really small area. So you can't really do surveys. You can do surveys, but they're much smaller compared to what we need for cosmology. And then the wide field instrument, that is the name of our infrared camera. So that's the detectors. There's 18 of them arranged in a mosaic like that. And so similar to JWST, it's in the near infrared range. So something like getting close to the optical, so 0.5 microns to 2.3. And then also a little quick comparison. I'll come back to this. But compared with Euclid, which is another space-based mission, so Euclid has a smaller, like half the size mirror, and it has two instruments. It has one visible instrument, which has a very broad wavelength coverage, and then also a near-infrared instrument, which is kind of similar to Roman's capabilities in many ways, but it is actually still a much smaller field of view compared to Roman's near-infrared coverage. And then Rubin, of course, is much, much bigger. So the mirror is 8.4 meters. And you also have, instead of talking about megapixels, you're talking about gigapixels. So that is, of course, like the biggest possible camera that you could have currently. And so, yeah, what you get from the ground, since it's much harder to send heavy things like that up into space, you really get that very wide area coverage. All right, so the power of Roman is not just because it has the large field of view, and then I added while in space, because clearly Rubin has a much larger field of view, but they're very efficient observations. And that includes something I mentioned before, which is slew and settle. So slew here means, when you're slewing to a different position in the sky, and settle means the amount of time that you need for your hardware to settle down and you can take a stable image. There's no Earth occultation. So that's compared to, say, the Hubble Space Telescope, which is kind of very close into the Earth. And there it depends, where you're looking, you can't look towards Earth because Earth will get in the way. And so there's more limited field of view for what you can actually see when you're that close to Earth. And then there's another thing here, the South Atlantic anomaly. So this has to do, I think, with the Earth's magnetic fields. And so that's where we have some region of increased ionized radiation that can also impact the data, depending on where you're looking. So then the other important thing is the stable PSF. So one thing to mention, so I mentioned all these telescopes that are close to Earth. Now, if you go to L2, which is much further away, that's where JWST is, and Gaia, and Euclid, and other missions in the future. That's where you have a pretty stable, like, say, thermal environment. It's away from, all the bright things, or as much as it can be, away from Earth. And then another thing is that it has a very rigid structure, and so that helps with the thermal isolation. You don't want different instruments having thermal signatures that like thermal backgrounds and things that might change how you can measure faint light from distant objects. Okay, and then the other thing is stable attitude control. So just how, if you can point it at a particular place on the sky very precisely. And then for the flux calibration, we have something that's called the relative calibration system. This is an internal subsystem to the wide field instruments, which allows you to shine flat fields just without any light coming in from the sky. So that's because we want to be able to carefully calibrate the relative flux levels. Just what is the response of the detector to some input light? And then on the right, it's just a comparison here between how long it would take Hubble, like how many different pointings it would take Hubble to cover the Andromeda galaxy compared to Roman. So Roman can do, that region in just like a handful of pointings. And for Hubble, it would take many, many times longer. And I think if you include all of the differences in efficiency, it's something like Roman is 1,000 times as efficient compared to, say, Hubble.
So, I mean, do you have filters as well?
Yes. Yeah, so we have, I think, 8 different broadband filters, and then also there's a dark element, so it's just covered up for calibration, and 2 dispersive elements. So one is a prism, so it's not as good resolution, but it gets a much wider range of wavelengths. That's really useful for the supernova science. And then there's a grism, so that's the prism with the grating. So that's a higher spectroscopic resolution. And that will be used for BAO and RSD, which I can't remember if I will talk about that later, but I will try to come back to that.
Do you remember the
Resolution?
yes.
Not off the top of my head, yeah, but I can find that. All right, so if we think specifically about the dark energy program for Roman, these are the main types of things that we're going to be doing. So supernovae represented on the right, so that's telling us about expansion history. Galaxy positions, so in that galaxy positions, I'm including acoustic oscillations, redshift space distortions, but also just general galaxy clustering. So, even using the photometric sample, but also using spectroscopic sample from the grism. And yeah, I can't remember if I say this later, so I'll say for the RSD and BAO, we're getting samples of, so this is another reason to do infrared, is that with the infrared coverage, we're sensitive to H alpha emission at redshift 1 and then O3 emission at redshift 2. So you can get something like, I think, 1 million redshifts for these galaxies at these higher, 1 to 2 range. And this could be, depending on what we learn over the next couple of years, it could be really interesting along with what we're learning from DESI. So yeah, if there's something interesting happening at that time in history, then Roman could be really helpful for that.
Can I ask you something regarding the filter? The Roman has its own filters, or it's similar to Chinese web?
Yeah, its own filters, but yeah, there might be some similarities, but I think it's a different vendor actually. And because yeah, there's a very particular optical system, and the where the instrument is located in the telescope is different from, say, JWST's instruments. There's probably a lot of kind of subtle differences. Okay, so and then galaxy shapes. So as you heard from yesterday, we're going to be doing gravitational lensing, and this is going to be another really important piece of information on the growth of structure, not just the expansion history. But together, all of these different science measurements then come together to give us the big picture of is it dark energy? Is there some modified gravity? Yeah, how does that look compared to other probes? Maybe one other thing I'll mention here is that Roman will do surveys, and I will come back to the process for how do we define these surveys. But I'll mention these 2 come actually from 2 different surveys, although the area will be overlapped. So the supernova survey, it has just a different kind of measurement that's required because you need to come back to reobserve the same field. So there's a time element there. It's not just static. And so that has kind of just different requirements on the survey properties compared to what we need for both the galaxy positions and the galaxy shapes. You know, we want to really as much volume as we can get. And so those, so again, they're kind of like two different parts, but of the same wide area survey. But there's the spectroscopic side. So, you know, we go across that survey area with the GRISM to get spectroscopic information, but we also go over that area with imaging. So that's, I'll come back to this, but you know, roughly there's what we call the high latitude time domain survey. So that's for supernovae, and then the high latitude wide area survey. But they're both high latitude because they want to look away from our galaxy. All right, so I don't have to dwell on this too much because you heard it yesterday, but you know, lensing, weak lensing in this case, causes galaxies to be aligned with the large-scale structure, and this is a 0.1% impact on the galaxy shapes, and so it's a really small signal-to-noise regime, and then, yeah, as you've heard, it's very sensitive to mass, density, and amplitude of fluctuations. But the really important things to remember for the measurement, from the measurement side, is that we need redshift distributions and we need galaxy shape measurements. All right, so again, maybe I go quickly through this, but you know, cosmic shear is specifically the correlations of shape and shape. And then, of course, galaxies also trace the underlying matter field, modulo galaxy bias. And then, yeah, so we have these like three different types of observables. I guess it's not fully represented here, but there's the clustering side, so position correlations, position and lensing, galaxy-galaxy lensing, and then cosmic shear, which is previous slides. All right, so I made this timeline of the surveys that were designed for cosmic shear, and there's some things missing from here, so it's not fully complete. But just to give you an idea of you know, where we were 25 years ago, almost 25 years ago, when we had our first detections of cosmic shear. And for a long time, you know, none of these analyses were done on surveys that were really designed for weak lensing. I mean, I think the surveys themselves were optimized the best that they could, but a lot of the telescopes that they were using at the time, they didn't really think about weak lensing as the science goal when they were actually building an instrument. And that's really changed. So, you know, on the right-hand side, all of these experiments, so Euclid, Rubin, and Roman, we already knew about cosmic shear. We knew what was required to make the measurement to some precision. And so, you know, when people were designing that instrument, that was really taken into consideration. And then, yeah, so I would say the ones in the middle, they were also, to some extent, also optimized for lensing, but maybe not as much as they could have been. And so that's, yeah, the improvements that we've made lead us to the current generation. Yeah, and then the last thing to mention here is that, as you are probably aware, we've gone from very small teams working on these measurements and, you know, individuals leading papers, and really it's a huge process coordinating across many groups. I mean, you have entire groups doing one part of the analysis, which I'll show you in the upcoming slides. But because of that, there's a lot of importance for how we all communicate. This is something Choi touched on yesterday. Just doing that coordination, I think we've learned so much. And so, yeah, I personally feel like that bodes really well for the future, but there's still things that we're also learning there, I think. Sorry. Yeah, so I didn't mention, we've also done cosmic shear with the Sloan Digital Sky Survey, and also with the Hubble Space Telescope. But yeah, those were much more difficult measurements. And also, yes, DESI is also ongoing. And then I'm not going to talk about SPHERICS so much, but I did work on it a little bit, and so that's going to be another really amazing data set. Okay. Maybe I'll go quickly through this. So there's a lot of steps on the road from when you get the images, and then you do some calibration. You're measuring things like the point spread function model, you're doing null tests similar to what Choi discussed yesterday. You also have to do image simulations. And sometimes if you can do some forward modeling and those simulations, that's really helpful as well. And then together, we're learning about the redshift distributions and getting galaxy shapes and selection effects. Okay, so then, you also want, for the clustering sample, you want some sort of identification of that and accounting for different selection effects there, as well as observational specific systematics. And then at the bottom is kind of coming at it from the modeling side, so thinking specifically about the covariance between your different measurements. And also you want to do some validation on mocks. And then you get these correlation functions, and then you do MCMC or maybe something else, as we may discuss. And then you get out some sort of parameter plot that looks like that. And so roughly there's kind of these main areas. And again, like each of these boxes, most of them have like entire teams working on them. So it is very complex. But it's, I think, with the current generation of surveys like dark energy survey, hypersupremcam survey, kilodegree survey, we've really kind of, we figured out a way to do all of this. So that's pretty good.
So this is using only photometry?
Yes, although there's some nuance in, when you get the redshift distributions, you're using information from spectroscopy or like validation with clustering redshifts. Yeah.
The clustering is 3D.
So in this case, I'm not considering the 3D clustering, but it could in principle, if you have a big enough sample of the like spectroscopic sample, you could be including that too. Yeah. Yeah, I mean, there are ways to then take, like, there's sometimes, people might do a hybrid thing where maybe the galaxy-galaxy lensing comes from spectroscopic foregrounds, and then the clustering that they use would be from just the clustering from the spectroscopic side. So that would be getting information from 3D.
When you do the 3 times 2,
yeah.
These are correlated because
yeah, so that gets taken into account hopefully in the covariance matrix. Yeah. Yeah, so there's
it's difficult to use that for 2 different lengths on one side of the lens and the other one. It's difficult to compute the covariance matrices.
I mean, it's been done. I mean, I think it is difficult. Like, it was a huge, actually many people here worked on that as well. So I think other people in the room have a better idea of exactly how difficult it was. But I mean, I don't want to say that it is very challenging and people put a lot of effort into it. But I think at least for the current level of
Carlos is there.
Okay, you should definitely ask.
I don't have any historical background to know how it's going to work. At least now it's a kind of a problem. So at least in the projected power spectrum. In terms of analytical.
It's a halo model based.
Analytical.
Theoretical. Analytic.
So back in the day, before that formalism had been developed, it was all done on some sort of simulation. But I think, there were some aspects that didn't fully capture. Like, it's hard to generate those as realistic a way. But it's still used for validation, to try to find some situation that you can put together in a coherent way and then test. And then, there is another, maybe what hasn't been fully solved yet in terms of covariance is exactly how we combine different surveys with the different information when they're overlapping. So that's, something for the future, I think, especially because, now we're starting to get all these different data sets. And so we do want to holistically. All right, and then the last thing I'll mention is that there was some sort of blinding done, and for DES, which is what is represented here, but for future surveys, they may or may not do it quite the same way. There were 3 levels of blinding for DES, and that's in general to kind of help against the experimenter bias. All right, so there's a few slides in here which I thought I would expand a little bit on what Choi mentioned, just for the one project that I was working on quite a lot. So this is the DES and KITS combination of cosmic shear, and just cosmic shear here, no galaxy clustering, no galaxy-galaxy lensing. And so this is where DES Y3, KITS 1000, and also HSC is represented here because we did also explore things with HSC, thanks to some of the HSC people who are contributing here. But the reason I mentioned the difficulty with the covariance is that actually for this analysis, we excluded any regions that were overlapping because of the difficulty of modeling the covariance properly. And there's even like a small boundary around where that exclusion is made. But in general, these are the stage 3 surveys, and similar to the stage 4 surveys, they also are complementary in many ways. They have different depths, different area, different systematics also. And so, so there's this these different complementary surveys, and I'm just gonna go straight to the results. And also because Anna might talk about some of these things a little bit, but here's what we found for omega matter versus S8 or sigma 8, which is basically it says tension with Planck. I would say no tension with Planck. It's actually pretty small, and whether that level of sigma gets you excited, I think it really varies across the community. For me personally, doing this exercise, I am not that interested in that number because and also Choi talked about this at length yesterday, small changes in how you do the modeling, including anything from priors to how it's parameterized, or what exactly is included, the configuration of your analysis choices. Small changes can actually, in what we found in our paper, can move the contours by more than half a sigma, even for things like changing the intrinsic alignments model. And so with that big of a change just for this modeling, I mean, I wouldn't say that. I think that we spent the time to come to some agreement on what we thought the best possible model was, but I don't think anybody would say we know that it is in general the best possible model. It's just based on what we can work with now. So that's certainly another area of exploration, is continuing to figure out what is the best model.
Is measured by the rule of thumb, or we use a particular tension metric?
I actually forget which one. I mean, there's multiple in the paper. Yeah, I'm blanking on which one this is though. Yeah, there's different distances, metrics, based on the distance, difference there, but to look that up later. Yeah.
I don't know about the changing the parameters and having different values. I had the impression, like when watching talks from Alexandra Mom, that actually, like, I think that the message she passes is exactly the author, right? That they have verified it doesn't change that much.
Change that much, I think, is maybe.
Sorry if that was
No. Yeah, I mean, I think we were seeing that it changes like close to half a sigma for some cases. So to me, that's a lot, or at least it's a lot as a fraction of what we actually see. So yeah, it might be a different like what a lot means and what that's relative to. Okay. It's not a lot in terms of, yeah, I mean, I would say in the general, like if we didn't do any of these experiments, and didn't know, like, we didn't have something that we were trying to resolve. Like, you know, we have information from the CMB and we're trying to understand whether this small difference is real. I mean, they're all small differences, actually, in some sense. But we're at the place where I think we're really getting down to the precision. And so to me, I guess the small differences are actually important. And maybe, yeah, to Alex, she might be thinking about it in the general sense. That would be my guess.
And one thing about that.
Yeah.
In a particular we did with the organical, and also we analyzed PS and kids together. I think what we found using the same scale cuts, it was again what you were saying, and what we heard also yesterday, that different choices they introduce shifts. Sometimes these shifts are like 0.2 or 0.3 sigma. So I think in the original analysis, shifts that were considered within 0.3 sigmas, they were considered fine. But what you realize in the end is that if you have many of these things, and we found out that about many, they can add up and actually produce, well, shifts that are larger than that. And we were seeing that with those scale cuts, including or not including Coriolis effects, was actually giving like 0.1, 0.2 sigma shifts, not that much, but like changing from halo fit to multiple spectrum emulator was giving already 0.3 sigma shifts. Changing the intrinsic alignment model was giving again 0.2, 0.3 sigma shifts. And in the end, you don't really know how they combine. So I totally agree that there is variability in the modeling that comes.
So my question then is, shall we keep only the linear particles?
No. But we should explore them.
Yeah, I mean, I think we need to do both, like, because people do focus on like large scales for some analyses, and then other people are kind of, yeah, exploring the small scales. And I think it'll be helpful to have all the analyses in parallel and try to develop that understanding of the small scales. Because that's also giving us a lot of interesting information that actually other people care about as well as us, like, you know, the galaxy formation and evolution sides.
One question also that I have in this regard is, I'm not working on length, but the impression being outside is that, you know, when doing all of these small scale modeling, you also lose a lot because of course it comes with next also branding, more parameters. So, so in the end, what's the status like compared to, is it worth it to go to small scale and well, how much we can see?
Yeah, so I think there are some papers that show, yeah, I mean, thinking about, you know, if you do a forecast of what is the precision that you get from those small scales, but then you have that larger parameter space. I think there are several papers that say it is worth it, like, because like for DES, for example, we're actually throwing out quite a large fraction of the data. So I think there's a lot of promise there. I think figuring out a situation where we're very comfortable with that modeling to know that it's fully robust, and you know that because again, yeah, different simulations have different results even for hydrodynamic. That's a good question, and I don't know. Yeah, maybe somebody else.
That's what I'd like to on that. At the moment, what we found with is very low scales with the space service is that if you are done for the value effect, that is the main aspect. If we forget about deep skies, we are now dominated by the uncertainty of them. But if we were able to do calibrate them with external probes like X-rays or things like that, you will get like 30% increase in percent power. So you will gain if you are able to calibrate those stuff.
Thanks. Okay.
Choi, yes.
Yeah, I guess yeah, I mean, I think the message to take away of these analysis choices matter a lot. is not like you should just give up. But and it's not reliable. I think it's just pointing to that we really have a huge uncertainty on the modeling side. And I think it's a bit what Carlos was mentioning. Like, I think the only way to pin down what is the right thing is to have other sort of data to constrain it. So I think, yeah, like we can keep doing these tests, but that wouldn't change anything unless we know what the priors are. So I think in the end, it's like hugely depend on the modifier.
So regarding necessarily with this, I remember last summer, not this year, the previous one, talking about all this and that people that Mateo mentioned before, with Elizabeth Krause and other folks in a conference. And one of the things that I don't know how much has been considered within the collaboration, but I think that like at least for the state that we are in right now, might be interesting, and we discussed at that point, was there are, like, for example, two models of intrinsic alignments that give, let's say, 0.3, 0.4 shift in sigmas. Is there a robust way to marginalize over that choice so that we have an account of like maybe a bit more conservative and over conservative assessment of the error bars that we know that we are taking whatever is like in the middle? Because a priori, I mean, I'm no expert here, but a priori, the problem that I can feel, for example, with that is that there might be some diverging prior volume there that like affects a lot, but it seems also that like it may get better assessment of what's going on with the with intrinsic alignment. So all of these choices, of course, like I think it was you two who mentioned this yesterday, all of them like make sense, but like we don't know which is the correct one. So is there a different way to deal with all that?
Scott.
So, two developments. One, so Alex Ramon and who's this? We have been with wrote a paper advocating or showing that if you just look at blue galaxies, then the IA thing kind of goes away. That's one thing. The other thing is former citizen here, but she's still currently citizen. Just Campos led a paper where she showed you could take the data before looking at the cosmology and see whether NLA is a good enough fit, you know, with that, it doesn't require TAP. You can make that choice before looking at stuff. So that's potentially be used.
Is this Jane? Not the concern.
Sorry.
Jamie McCullough. I think
The studio just got out saving.
Oh, it wasn't me. Okay.
Um,
I think we did baryonic.
yeah,
So, yeah.
well, I'll add, like, so formally CAT is, covers NLA, so NLA is a subset of. So I think, and that way there's not like, if you use CAT, it's always right, there are prior volume effects, but I think that's a different problem, that's not the modeling problem. And then I like what Scott's saying, so I think in the end, we do need direct measurements of like, we can't simulate things out of this, right? So I think that using blue galaxy or certain kind of galaxy, or like really nearby, there are kids measurements on these things, right?
Mm-hmm.
So you can directly measure what the value is and then see what model it fits. So I think, yeah, in the end, that's probably same for variance.
But I have two questions on that. So Enrique Rubira is there, so he can clarify. But doesn't the EFT people say that TAT is like a kind of ill-defined model? And second, didn't Nick and Stephen in their EFT paper show that even NLA is kind of a terrible fit to the 3D spectroscopic data? Which does not imply that it's bad for weak lensing, but some of the plots were a bit striking for me.
I just don't know what that is. But I heard from Mateo that it's a bad model.
Not at all.
I think I totally agree with William. There are these models. There is Nick. There is also Francisco Marion. That is developing something similar and really testing thoroughly these models in simulations. I think, but I also just have to wait for Nick. The problem now is the applicability of these models. They are very promising, but maybe not still at the point in which they can be included in a prediction analysis. I am more familiar with the one of Francisco, and for now there is no emulator for that. So if you had to compute your intrinsic alignment for each cosmology you are testing, good luck with that. But I mean, now I got the ball to Nick. That is not even here.
I think this is an excellent topic for discussion, but I think it's going off a little bit
Yes.
from the main. So I suggest to keep this as a discussion topic. This is a very hot topic. So who wants to talk about this, Matteo? No, Nick.
I think there's a little line here of spirit. So in Italy 2 weeks ago, Richie Ivanov was giving a talk, and he said he was showing results in which he uses simulation-based priors into EFT sense. And this amazingly gives better results than simulation-only results. So I was quite impressed by these. I think we should include something like this in discussion.
But we have discussed on simulation-based inference, which is different from simulation-based priors, but maybe.
No, definitely. But even, I mean, to address the question, I think priors, like that you think simulations and run them and find priors in EFT seems already quite good. Or
we should talk about this. We should talk about
it.
Yeah.
Sorry. So the Misne wrote a paper with they found that as long as the model is for projected things, is 10% accurate, that's fine. So I'm not sure if NLA of that, but that's probably easy to super clever. So if you don't need the best and super best tips alignment, I would know tips alignment.
Yeah, no, this is a great discussion. And maybe I won't go through all of this slide because I think it captures some of what people are already thinking. But yeah, the last thing I wanted to mention for the intrinsic alignment side is that I think Choi was saying this at the end, that we actually do have a lot of measurements that over the years, people have been trying to use the measurements themselves to constrain the models. I think so far there's maybe not a lot of enough signal to noise yet to really put much constraint on those models. But I think that's the other, in addition to thinking about the approach of the modeling itself, also using that data, additional data to constrain it, or self-calibration, as the paper Scott was alluding to. Okay, so yeah, the general challenges from the modeling side, I think, are the baryons and the intrinsic alignments. But there's a lot of cool things people are doing these days to make some there. All right, so yeah, now we get to stage 4, dark energy surveys. So we have Euclid, and that's 1.2 meters, and then has a visible and infrared information, and then it's really kind of like shallow, but wide. So it's really going to get a lot of coverage of the sky itself. That launched, so this is a little bit old, so July of previous year. So it's now been taking data for like a year and a half. And they've started their main survey as well. I'll touch back on this, but that's really exciting. And then of course we heard from Choi yesterday about Rubin. So Rubin's got first light with the commissioning camera, and then the actual operations will, after the main camera, LSST cam is installed, then the full operations and survey will happen toward the end of 2025. So Roman, I already covered this, so maybe I won't go too much into depth, just to say that we are currently on track for readiness of the entire mission at the end of October 2026. But you might also see a date of May 2027, because that's the date that NASA has agreed to launch the mission by. Okay, and then comparing these on kind of a different parameter plot. So we have the wavelength coverage on the x-axis here, as well as the depth, something about the depth on the y-axis. And so, yeah, so LSST is that blue there, so it goes extremely deep. And then Euclid is up there. So yeah, it's fainter as you go down and a brighter limit as you go up. So Euclid is shallower in terms of depth. There's also some sort of label indicating the PSF size. And so yeah, basically, yeah, Roman is giving the complementary dark or high depth part of this plot on the right-hand side. Okay, I'm just going to very quickly mention there's a lot that we're learning from Euclid. So Euclid, because it's also in the sky, I think there are a lot of useful lessons learned for Roman. They actually had quite a lot of trouble during the very early stages, so commissioning, et cetera, where they were discovering all kinds of things like scattered light in their images and some other things that they were able to fix. Some of it they're not fully able to fix, but at least they can develop ways to mitigate it, at least in analysis, or change their survey strategy. But as just to mention, there are things that you can never imagine from testing on the ground that will magically appear when you're actually trying to take science data. And yeah, so there will be some period of that, I would imagine, with Roman.
Ami, don't they have water in their mirrors, which is causing trouble?
Yes, also, yeah, so they have some sort of like ice buildup that they're trying to deal with. But I don't know the latest on that. Yeah, you can do, I mean, when you have your observatory, you do things like, if you have some ice buildup, then you try, heating up some parts and, getting rid of it and seeing how to change the thermal conditions to make those issues go away. So there's different things that these missions are designed to try to, dial some knobs to see if it can help with those kinds of issues.
Yeah, ice will away.
Did it go away? Okay. Oh, right. Okay. I'm now remembering. So there's a talk from Misha Shermer that I think showed there was like some plot of the ice versus time, and then all of it, it just like went away after some period of time. So I think they're not impacted by that currently. But there might be some understanding of exactly how that came about and how to prevent that in the future. All right, and then just a quick snapshot of what we can get in terms of like W naught, WA. So these are from Tim Eifler, and several other people who do Roman forecasts. So these are, I think, in the process of being updated, and Vivian's probably working quite a lot on this area. But yeah, these papers are several years old now. So there's a lot that we've learned since then. Plus there's like a survey definition process going on now, which will tell us exactly what is the area and what is the information that we're getting from surveys. All right, so I think maybe I will go very quickly through this second to last section. Just so the takeaway from this slide is that to measure the galaxy shapes, we need to know the PSF really well, which also includes things like detector effects and also the wavefront error. So, if we had a perfect plane waves, then we wouldn't have any wavefront error, but there are optics on board. There's the angles at which the light is passing through and bouncing off things that mean that you might not have a perfect wavefront. And so that has to all be taken into account when you measure the shapes. So, okay, I'm going to skip the detector effects section here, but there are a lot of detector effects. We need to know the PSF to very high precision. So there's some numbers that are sub% there, significantly less than a percent. And so, yeah, there's a whole bunch of investigations understanding what the detector effects are. So maybe I will just skip to
Can I ask you something?
yeah.
Is that something that I was talking to Natalia Rosquera that she does build that up, and something that she was mentioning that some people are discussing in the field of level, that it would be interesting to have like new instruments that add those
be differential of all the three groups. That way it will be easier to model all these effects and do the field level. Is something that is being considered at
Yeah.
all, or is like very futuristic?
Yeah, that's a good question. I don't know
Okay.
much about that, but I mean, just from you know, just dreaming about things like that, that would be,
Okay,
that's
it's not
like, it would
something
be
that
great. But yeah, I don't know if that's in any way realistic or,
Okay.
yeah, whether people have been thinking about that.
Okay.
Yeah.
Thank
Okay, so I'm just gonna put up a plot here of, we've been looking, okay, so we all, or not all of us, but some of us are interested in correlation functions, 2-point correlation functions. You can measure correlation functions also on detector pixels. So looking specifically at effects that might propagate toward adding to correlation functions from cosmology. So we don't want that, right? So we want to characterize, like one way of characterizing these detectors is to use those correlation functions to study the detector effects themselves, try to isolate that. So that's what we've done over the past many years, trying to isolate things like, so brighter, fatter effect is one thing that also affects, it will affect LSST as well. So this is where you have a lot of electrons or electrical charge building up. And so you can imagine that if you have a signal building up in a pixel, the probability that, if the signal level is high, the probability that the next electron or photoelectron will fall into there, it might be kind of repelled off to the side. And so that means the brighter the source, the more spread out it might be because of the electrical self-emission. But you can imagine if that's happening in the detector, then that's not really telling you, like you have to account for that before you can measure the galaxy shape. And then there's another effect specific to near-infrared detectors called interpixel capacitance, and that's like a parasitic coupling between any one pixel and its 4 nearest neighbors. And so there's just some sort of connection, and that also has to do with just the electric field within the detector itself.
So you're testing this in case of saturation for bright stars, this kind of effects.
Yeah, you can do that. Yeah. So that's how we did it for DES and also for, I think for LSST as well. You look at the effects of bright stars, and you might have some sort of model for what the brighter, fatter effect, like physical model of like how that should spread out the charge. And I guess, yeah, for something like LSST, what they've done before they got data was to run simulations and try to measure that on simulations. But yeah, you can measure some sort of correlations on stars in actual data to see what that is.
Change the value on the head of this kind of effects, therefore could translate to the correlation functions.
Yeah, well, it changes your PSF model, and so related to, so for example, Choi yesterday was showing, some of the way of measuring the impact of that, the PSF model issues to the cosmology is, you measure the correlation functions of between like the star model and different correlations there. So that any bias, I guess, in that PSF model, either the size or the shape, will propagate to the bias in cosmology. Yeah. Okay, so yeah, we've made maps of these kinds of effects across, this is for a single detector, and it's grouped into superpixels. And so each square there is like 128 by 128 pixels. So yeah, I mean, the main thing is to identify how these effects vary across the detector, because I think spatial variations, those are the kinds of things that can impact like coherent correlations for the when you try to do the cosmology measurement. So these are all just things that we have to understand, and we'll use this for calibration later. Okay, I will talk a little bit about this because I think this is also very important. So we're currently simulating joint Roman and Rubin information. And so this has the same underlying physical universe coming from the data challenge 2. And then Ruben has their, how would Ruben see this through their eyes? And then Roman has similar thing, how would we see this through Roman's eyes, and also taking into account things like the different detector effects and such. So this is a picture from a paper Michael Troxel led in 2022, which is just, I think this comes from the data set, which is 20 square degrees, but we actually have a much larger data set, which the paper is in prep now, and that will be released later this year. But that one simulated more specific fields that Ruben will definitely cover, and I think Roman will probably cover too. But yeah, it's just an example here of what you might see. I think I had there's a plot somewhere which shows this particular image, I think in Ruben, where it is very clearly blended. Whereas in this image, you can see that there are separate objects there. So that's one, area of research that people are looking into, is just understanding the blending effects between Roman and Ruben, and we had some discussion about this yesterday.
I mean, how does the galaxy density compares to Ruben and LSS2?
Yeah, it's a good question. Yeah, I mean, Roman density is, I think, higher for this particular image, but actually, I can't remember for the Ruben image simulations, actually, if that's the full 10-year or not. Yeah,
This is
do you remember? Yeah,
So they didn't resimulate the,
I don't think so.
that'll be 5 years.
5 years, okay.
Maybe.
Yeah, so that, I think it is then probably significantly less dense. But I don't remember do you know what the density is for?
So I think for, Vivian probably has it on the top.
Oh yeah,
Mind.
that might be,
What is the
Vivian,
number?
do you know the number density for LST 5-year?
Or just Roman.
So I think Roman would be like 50 or 50 to 60.
Yeah, for Roman, I has 40 something in my mind, but I might be wrong. I can check that in a few minutes. Let me.
Per arc square.
The one sample for Rubin is supposed to be 40.
Okay. For the
But yeah,
for the 5 year?
full depth.
Full depth. Okay, so then it's much less. Yeah, so here for this particular instance, I would guess Roman is around 50, and then LSS2 maybe around like 20, 30.
So, and the blending is less, I mean, it's less important for Roman because of the resolution.
That's right. Yeah, so it's something like 0.1 arc seconds per pixel. So that gives you and the PSF is much smaller. Yeah.
So
to the level where, go ahead.
So for LSST, my forecasts here, at the source, it's around 27 galaxies per arc minute square, and for Roman, it was about 51. That's for the sources.
Thanks. Okay. I think I had a thought in my mind to also mention, but yeah, it's gone. All right, so then I'll talk a bit about the Roman status, but I'm going to go very quickly through this because I'm already over time. So yeah, I wanted to mention what's been happening in the past year or so is that all of the individual subsystems, including the wide field instrument, so again, that's our infrared camera, have been tested to very put through an environment which is kind of mimicking space-like conditions. So it goes into a thermal vacuum chamber. So this is an example of one of the thermal vacuum chambers it goes into. That's in Boulder, Colorado. So BAE Systems, which used to be called Ball Aerospace and recently changed to BAE. And so this is just to give you an idea of the scale of the whole experimental setup just for the infrared camera that's being wheeled into this chamber. So what happens is that they pump this down, so vacuum sealed and then cooled. And then there were 2 campaigns. Yeah, maybe there's a slide here. Both were 2 months long. And so the first of these campaigns, so TVAC 1, that's to test, like to get a baseline, just see, is everything performing as it should when you turn it on? And if so, what is the actual signal that you get from there? And then in the middle, so that whole setup got taken out. They shook it, and then they also blasted sound at it. And that's because when it's launched, it will be in a very turbulent environment, vibration, it's really loud. So they want to mimic that. And then you do a TVAC 2, so it's another 2 months test to see, did anything change from TVAC 1 after that kind of violent interaction? And I always am entertained by the contractor that they bring in to do the sound blasting. So it's a company called Maryland Sound, and this is a company that's known for hosting big rock concerts. So they have a history, of being very good with the sound. Yeah, so I always find that a little bit entertaining. And so TVAC 2 then also does a full characterization. So we're trying to learn really, how does all of the different parts of the instrument perform? And some of this data will be released to the public. So there is an archive, and I haven't mentioned this yet, but our Science Operations Center is the Space Telescope Science Institute, which will be responsible both for the data processing, but also the archiving. Another thing I may not have mentioned yet is that Roman data will be immediately released to the public. So of course it takes some days, to acquire the data, probably run it through the processing pipelines, but there's no proprietary period. And this is both, I think, a great opportunity for everyone in the world. But then, yeah, I'll come back to this also being maybe a little bit of a challenge as well in a future slide. But all of this testing is important for how we do the calibration in the end. I'll skip through most of these things, but here's an example of in the test, the TVAC test, we put a really bright source mimicking a bright star onto the focal plane, and then we do expect in the actual operations, because the camera's very wide field, as you may remember, it's almost impossible to avoid extremely bright stars that will saturate immediately. And so we do want to know what does that actually look like on the detector? Does it ruin basically everything nearby? Is there some way to do, if you have a bright star and you actually care about things that are very close to the star, can you still recover information on those things? So yeah, I have some colleagues who do like high contrast imaging, thinking about like planets and other dimmer objects near bright sources. And so, yeah, this was a test that we're using currently. And so, yeah, the analysis is ongoing to see things like, so an example is persistence. So persistence is a detector effect where something really bright, it kind of like burns in the memory of that brightness, so that even when you reset the detector, take another image, you might still see some kind of pattern of that bright thing. So yeah, persistence is like a memory effect. And that could be really important because, we're going to be surveying the sky and we need to know if there's any bias from that leftover light. So that's the kind of thing we're hoping to learn from this data. And yeah, I think that will be useful. Okay, so yeah, just some, this is a video, I think that's available somewhere online or on social media. So this is just looking around, or actually maybe I did this one, I can't remember. But this is looking at a big clean room at Goddard. So this is basically everything is there now. These are all different aspects of the spacecraft. So here's a static view. So Solar panels are up there. That's the communication antenna, high frequency antenna array there. This is part of the deployable aperture cover, which is, I'll show you in a second. It's sort of like a protection from the sun at the top. The spacecraft bus, which is kind of like the central nervous system of the observatory, is a hexagonal thing kind of in the back there. It has something like 40 miles of cables running through it that connects both to the communications back out to us and then to operate the rest of the observatory. So yeah, all kinds of.
And the mirror?
Okay, so the mirror, and yeah, I put a picture of that to sort of, you can see, the solar panels are up there. You can kind of see that shape. The deployable aperture cover here, that's what that will look like. Currently, it didn't have the material on it, but that will be the top thing there. Okay, so that's the mirror. That arrived a few weeks ago, and actually has now been integrated on top of this, what we call the instrument carrier. Right now, there's a coronagraph, which is our other instrument, which is already installed on the other side. The wide field instrument is the thing just above that kind of has that tall rectangular shape at the top. That will come on the side here, instrument carrier. And then yeah, this mirror is already on top of that thing. Thanks. Too short to. So this will sit on top of here. The wide field instrument will come here. And then all of this will go on top of this spacecraft. Okay, so I think this is maybe the last slide, yeah, main slide. I said I would talk a little bit about the challenges and opportunities. The calibration is one of the main challenges. So that's how we actually realize the promise of. So I said, Roman is really designed to tackle some of these systematics. And compared to Rubin, as we've discussed, the key thing is that it's above the atmosphere. And so we're just getting different information on that, from that point of view. But of course, it's really hard to acquire the same amount of data that Rubin will get from the ground. So really, they are highly complementary. Yeah, but it involves a lot of testing and analysis of the testing. But a lot of what we're doing is actually the same kinds of things that we're doing when we measure cosmology, like doing these 2-point correlations. And also understanding, how forward modeling and simulations of these effects. So another thing that I didn't really talk about too much is that, so like Vivian and myself and Choi are all part of what we call a project infrastructure team. So this is a team that's funded by NASA to build the infrastructure before we get the data in 2 years, or a little longer than 2 years. And that includes everything from, if you remember the huge, scary pipeline flowchart, that includes everything, all of the software that will enable the measurements and do the calibration, shape measurements, photo-Z, et cetera. But also it includes all of the tools to do the inference. So this is something that Vivian's working quite a lot on, and Choi and others, is then taking the measurements and applying the model, and exactly how you do that with, say, a likelihood analysis or likelihood-free analysis, et cetera. These are all things that we're thinking about as a team. But then, yeah, I wanted to mention, we do actually have a limited amount of time before the data is collected, because as I mentioned earlier, there's actually no proprietary period. So what I think is really important is to build the groundwork for that, at least to the level that, given what we know from ongoing surveys, incorporates all of those lessons and helps us, along the path to having some unbiased cosmology. And then there's the broader community. So Roman is really community-led in many ways. And one of the main ways is that the survey definition is going through this process, which is there's a little diagram down here of the timeline of it. There were people who expressed interest in being on committees for either the high latitude wide area survey or the high latitude time domain survey, also the galactic bulge time domain survey, so that's for the macrolensing. There was one committee recently formed that's a galactic plane survey. So that's another kind of near field observing survey. And a last thing is to mention is that when Roman is up there, it'll have something like 20% general observation time. So people can apply for time. And so this is another, I think that's a great opportunity just to think about what kinds of science can be done that benefit from that really high resolution wide area. Because it's not going to be the same science that people are doing, for example, with JWST or Hubble. I mean, there might be some overlap, but what we really care about is things that benefit from those statistics. And so there might be something related to fundamental physics or cosmology that we can think of. And I also put some links to, there was a call for white papers and also inputs into what the surveys should be designed to do. And so some people have already been thinking about that. And so if you want to see what they've been thinking about, you can go to those websites and look at the actual papers there. But in general, oh yeah, so I didn't finish my thought on the community survey definition. So right now, they're working with a lot of understanding, they've been doing trade studies of like the actual area and depth and which filters will be observed in, et cetera. And so the committees are deliberating now, and they're about to send in a final report to the Roman project. I think, yeah, I heard, so the high latitude wide area survey, I think, has a couple more weeks, maybe less than 2 weeks to deliver their final report. But it's sometime early next year, or maybe mid 2025, that we'll actually know exactly what are the data that we're going to take. But it's complicated because we have multiple, we actually have 4 different surveys, and they have different requirements on, some are looking at the galactic bulge, some are looking at high latitude, and they just have different requirements for scheduling, et cetera. And we're fitting that into 5 years. But then there's a further opportunity after that 5 years in which Roman will almost certainly be taking data and up there for, I would guess, at least 10 years. So there's another 5 years after the main survey that is still completely up for discussion on, what is the interesting science at that time that will benefit from Roman observations. And I've heard, so there's actually a white paper that was actually suggesting, let's do the opposite of what the high latitude wide area survey is doing and do a full sky single band, just like getting really something that you can cross correlate with other information that we have from the full sky. And there are a lot of science cases that benefit from that. I would say less weak lensing related, but that could be a great candidate for something that we do in the next 5 years after the first 5 years of surveys. So I would say there's quite a lot of opportunity there to think about, what kind of science cases we might be able to tackle. So yeah, I think that's pretty much it. Let me just put up the, yeah, just leave that up there. Thanks.
Thank you, Amy. So we're actually very late. So
Yeah, sorry.
So no, it's not your fault. I think it's very nice to have discussion. So I suggest just go for coffee.